Sir, your mic is on mute.
Yes.
Okay. Sorry for that. Yeah. So what I was talking is about the velocity saturation effect. This is one among the effect that we have under the secondary effects. And velocity saturation effect is something like when the electric field between the source and the drain attains a particular electric field, which we call it as a critical electric field, the velocity of the carrier becomes saturated. So due to which there are a few things that happens to our device IV characteristic graphs. Okay, one of the major thing is that our device will enter into saturation regime well before the value of VDS is equal to VGS minus VT. Okay, because in the long channel device, we always assume that the transistor enters into saturation regime the moment the value of VDS is equal to VGS minus VT. Okay, so that was something a kind of a well-defined voltage by which I can get to know whether my device is in saturation or I'm in the linear region. Okay, but right now when we use a small channel device, what happens is that this phenomenon never follows. Like we can't completely define that our device enters into saturation the moment the VDS is equal to VGS minus VT. But in short, the device enters into saturation for value of VDS that is even smaller than the value of VGS minus VT. Okay, so due to which what happens is that we have an extended saturation regime. And the second physical phenomenon that happens is that the saturation current is proportional to VGS minus VT. Okay, so this is something which is different from than compared to our previous characteristic graphs. Okay, where the saturation current for a long channel device was proportional to VGS minus VT the whole square, but right now it is proportional. Okay, so due to which there is an equal width when there is an equal increment in the value of VGS. Okay, so this is something that we had addressed in the previous class. And also because the ID sat is a function of kappa of VDS. Yeah, so here is this. Okay, so since because the ID sat is basically a function of VDS, what happens is that the current that we would get for a short channel, a value of VDS which is larger, the kappa value we always know that it will be less than the value of 1, due to which the current also gets reduced. Okay, so these are some of the physical phenomena that we were addressing in the previous class. And today I just want to show you about this characteristic graph plot. Okay, so I just want to plot this ID versus VDS graph through simulation, and also if possible I will try to plot ID versus VGS. Okay, this simulation is just a way to explain the things. Okay, so it's not a part of your theory course, but it's part of your lab. I guess right now you could see the screen, right? A different screen. Yeah.
Yes, sir.
So there are a few setups that I have to do.
Yes,
just bear for some time. So these things you will be learning later on during the course. Okay, so I'm just trying to show only the graph part of it. So you don't need to worry right now about why I'm setting all these things. So now that I'm just going to plot ID versus VDS graph, okay, and the value of VGS that it has taken is 0.6. Okay, so I have just defined those as a variable, and right now we are varying the value of VDS right from 0 to 1.2 volt, and I have kept the value of VGS to be around 0.6 volt. Okay, yeah. So this was the carrot that we had, and I also wanted to plot for different values of VGS. Okay, not just for 0.6 I just wanted for different values of VGS. So what I do is I have to perform something known as parametric analysis, and I'll just pull out my VGS, and I would vary the value of VGS from 0 to 1.2, maybe 6. Okay. Yeah. Okay, so these are some of the caras, and as you could clearly see that there is some sort of quadratic nature when the value of VGS, even it's a function of VGS as well. Okay, so but as you move on, the spacing that we have between these two lines. Maybe I'll change the background. Okay. Yeah. So again, there is something known as mobility degradation, which happens because of the vertical electric field that is created between the gate and the body. Okay. So again, it's a function of both the mobility. So in this case, you could see that the spacing that I have here is as similar to what we have here. So maybe I have to do a number of. Let me just try to step this one. Steps. And let me specify the step size as 0.1. Okay. So I'm just incrementing the value of VGS in steps of 100 millivolt. Yeah. So I hope that right now the graphs are clear to you. You could see that the spacings that you have is almost like a kind of equal spacings when I try to increase the value of VGS in steps of 100 millivolt. Okay. Is the graphs are clear?
Yes, sir.
Yeah. But for low values of VGS, obviously it follows some sort of quadratic relation. Okay. But as you raise the value of VGS, then again what we have is something known as mobility degradation. That is again one more effect. Okay, that I will be discussing now. But this is what happens when we try to plot it. Okay, so we have equal spacings in the kind of saturation current. Okay, and there is no appropriate region where I can visually see the linear region separated out of our saturation regime. Okay, it's almost like a kind of linear graph. Okay, so something like a kind of a smooth graph that happens here. Okay, so it becomes very hard for us to actually define whether the transistor is in saturation or in the linear region.
So this is for chart panel transistor.
Yeah, this is for 45 nanometer. Okay, the length and the width of the channels are specified here. Okay, so here in this case, the length of the channel was 45 nanometer. Okay, now we can actually mimic, but it's not a real device. But what I can do is that I can just make this as something like 1 micrometer. 1 U means 1 micrometer, and I would increase the width to, say, for example, 10 micrometer. Okay, and there will be a slight change because the thickness of the oxide remains the same for 45 nanometer technology. Okay, so due to which there will be some sort of mobility degradation effect. We can't really model a long channel device just by changing the length and the width of the transistors, but still we can certainly see some sort of changes that is happening. Okay. So what I know is I did the so we'll have both of side by side and you'll see the long and the I guess it is this right. Yeah, so right now the value of just 1. So now what is up? I'll just make this as 1 micron as the channel length and 10 micron as the width of the transistor of the channel. And let me just get back to parametric. Yeah. So again, we are not entirely changing the technology. We are reusing the 45 nanometer technology itself, but with higher length and width. Okay, so certainly there will be some sort of differences, but you cannot expect some sort of quadratic nature that I was showing earlier. Okay, so we have to use the real technology for it in order to get the effect. Okay, yeah. So the one towards the right. Okay, so this is something for a kind of longer channel. Okay, and the one towards the left side is for the shorter channel. Okay, so you could barely see that there is a kind of spacing becomes higher and higher. Okay, whereas the spacings here are almost equal, whereas here there is some sort of impact that you could see. Okay, I guess more than this we can't really talk about this just with 45 nanometer. I have to use a completely different technology to talk about it. Okay, so that whatever we study in the theory with quadratic spacing, you can really see those quadratic spacing only for technologies which are at least a minimum of 500 nanometer or more than that. Okay, 1 micron technology. If we have, then those technologies can be utilized and we can do the simulation in order to get the characteristics that we see normally in our textbooks. Okay, this is just to show how the graphs have been plotted, and you could also see that the saturation region barely happens for a value of Vds that is more than a certain value, okay? Whereas in this case, you could see that the device almost enters into saturation regime for even for small values of Vgs. Yeah. So now I'll just switch over my screen. So the next type of impact that I wanted to discuss is about mobility degradation. Now, we have already seen something known as velocity saturation effect, and that velocity saturation effect happens because of the lateral electric field. That is the field that exists between the source and the drain, okay? But on the other hand, what we have is a field due to the gate as well, okay? Because we know that the gate certainly has some sort of potential which is greater than the value of Vt, okay? So this will actually create some sort of field across the oxide, okay? Across the thickness of the oxide, we have some sort of electric field, okay? Which is a constant electric field that we have studied when we discussed about the CV cara, right? Yeah. Now, even this field will create some sort of impact. Now, what we wanted is the free carriers. Let me just choose an NMOS so that I have a p-type as my semiconductor. And once the value of VGS is greater than the value of VT, we know that it pulls out all the electrons and it creates some sort of channel here. Okay? And then we also know that we have some sort of depleted region around this entire segment. Okay. Yeah. So now what happens is that these electrons has to move from the source side towards the drain side, okay? And this is our integrated operation. But what happens on the other hand is that the value of VGS creates an electric field, which we call as a vertical electric field, which is given as Vg by the thickness of the oxide, okay? So now as the technology shrinks down, the thickness of the oxide becomes less than nanometer, okay? I think at the atomic scale, you will find this thickness of the oxide, okay? So this in turn creates some sort of huge electric field, even for small values of VGS, okay? And that creates a very high electric field. And due to which one could actually model the mobility of the carrier that is effectively being disturbed by this vertical electric field as something like mu naught when there is no field that causes the motion due to the vertical field. And then there is some sort of eta factor, okay? This is something like a kind of empirical factor multiplied by the VGS minus VT, okay? So as we raise the value of this VGS minus VT, effectively, what happens is that the mobility of your carrier becomes slow, okay? Now this can be, again, can be shown some sort of with a comical video, okay? As something like this, okay? So this is a kind of a reporter who just wants to report something, and he is trying to put himself stand against the strong wind, okay? But he couldn't able to resist. So what happens is that he couldn't able to move between the source and the drain because of the high vertical field towards the storm, okay, that flows, okay? So that makes him to collide along the wall, okay? So it is something like you, okay, let me stop this video, okay? So you got some sort of an idea, okay? So with this idea, let me try to mimic this cartoon, okay? So you have some sort of wall, okay? And you want to run between the source side towards the drain side, and you want to have something like this. But what happens is that there is a vertical field that is coming from the other side, something like a kind of blower, a big fan, okay? Okay, so you have to assume that this is a fan, okay? So there is no other way. And this fan is actually blowing at a very high speed, okay? So due to which, what happens is that this person, his original speed would be much larger, but just because of this blow, his speed would be reduced. And in general, what happens is that he collides at the interface between oxide and the semiconductor, okay? Rather than he tries to move freely, he's being hit on this interface. So it is something like you are trying to run close to the wall. So what happens is that the speed at which you want to run actually gets slowed down, okay? Rather than running in a very free space, you are trying to run in a very cumbersome area. So due to which you cannot run fast, okay? And this is the type of impact that we call that impact as a mobility degradation. This happens because of the vertical field created by this gate potential, okay? So after this, what we have is something known as channel length modulation. We have already discussed about this channel length modulation effect in the last couple of classes. I'll just revise, okay? I'll not do the derivation here. Now, under this channel length modulation, I'm just going to assume that the length of the channel is quite high. Okay, so in the sense we are talking about a saturation current for a long channel device. Okay, so we know that that could be written as IDS saturation, and that could be written as half K dash W by L VGS minus VT the whole square. And effectively what happens is that the length of the channel is becoming tapper and tapper as we rise the value of VDS. Okay, so this is the channel that I'm trying to mark here. Okay, so this is my channel area where I have filled with all charge carriers within this zone. Okay, and this happens when we have VDS that is equal to VDS sat. Okay, and as we rise the value of this VDS beyond the value of VDS sat, say for example, I am talking about VDS1, which is greater than the value of VDS sat. What happens is that this channel is actually getting tapered further. Okay, and effectively the length of the channel has got reduced where I have filled with carriers. Okay, so this region is currently been filled with carriers, but there is a region where I don't have any carriers here. Okay, so this particular region is left over with no carriers here. Okay, so the effective length across which I have carriers has become something like del L, and this is my total length of the channel. Okay, and effectively what I have here is the L minus del L. Okay, and because of this we derived and showed that it could be written as half K dash W by L into VGS minus VT the whole square into 1 plus lambda. If we really see, this delta L is actually proportional to delta VDS. So this delta VDS is nothing but it's a voltage that goes beyond the VDS sat. Okay, so I could write my VDS as a potential that is offsetted by this VDS sat plus any extra potential that I'm giving can be written as delta VDS. Okay, so what happens is that we were trying to use this relation, and then later we wrote this delta L to be equal to delta VDS, but we introduced a constant which we called as lambda prime. Okay, and later on we also introduced one more constant which was written as something like, and due to which one could write something like delta VDS. Okay, so now what happens is that this is a kind of Cara where I'm trying to plot with respect to delta VDS. Okay, so when you try to plot the saturation current IDS, okay, in terms of delta VDS, now for a value of delta VDS that is equal to 0, we know that we have some sort of saturation current, and that could be defined only by this particular quantity. Okay, so this quantity, let us assume some value for it, and along the y-axis it has some value. Now as I raise the value of delta VDS, what happens is that the lambda gets multiplied with the increase in the value of this delta VDS, and due to which the graph would normally look something like a kind of tapered line. Okay, now we don't want this Cara to be plotted along the axis where I have delta VDS, but what I wanted is a plot of IDS versus VDS. Okay, I wanted a plot that's supposed to be running across the value of VDS rather than the value of delta VDS. Okay, and due to which I need to translate each and every point that I have here onto this particular plot. Now, in order to translate from here to here, I have to make use of this equation where VDS is nothing but, it is defined as delta VDS plus VDS sat, which I wrote it at the beginning. So the 0 point that I have here, when the value of VDS, delta VDS was at 0, I had this particular point, and this point has to be mapped onto this graph, right? So when you try to plug in the value of this, maybe I'll use a different color. Okay, so this point, I want to plot it over this VDS graph. Then what I do is that I just plug in the value of 0 that I have here over here. So now what happens is that for this current value, our VDS supposed to be equal to VDS sat. So which means that this particular point is actually mapping onto this particular point where the value of VDS is equal to VDS sat. Okay. Now this point, again, you try to plug in the value that you have here. Okay, this value, let us assume that it is delta VDS1. So that delta VDS1 you would plug in here, and due to which that same similar point would be marked over here. So when you try to join all of these points, the same chara would be translated on this particular chara. Okay, and to define this current, I want to rewrite this saturation current. Okay, so how will I rewrite this? I have to change this delta VDS in terms of just VDS. Okay, so my saturation current that I normally use to plot it against IDS versus VDS can be rewritten as something like half K dash W by L VGS minus VT the whole square, plus in order to plot on the axis of VDS, I have to write it as lambda times the of VDS. Clear? I think there was some sort of discussion around this particular point, and this is what I was about to define when you were asking about this particular doubt. Okay, so I want to translate on different graph. Okay, and due to which this delta VDS has to be replaced with VDS so that I can utilize in the graph that I was trying to plot ID versus VDS. Clear? Yeah. So after this, we have.
But this expression is valid only after VDS sat.
Yeah, of course. But we also know that when the value of VDS is less than VDS sat, I will not use this current equation. I will be using the linear current equation, okay, which is defined as K dash.
Oh, yeah.
So I'll be using that in order to plot the remaining part of the graph. So now let us talk about the other phenomenon that we have is about the body effect. Okay, so probably you might be already familiar with this body effect. Now, this is a kind of physical phenomenon that happens whenever the source and the body are at completely different potentials. Okay, so what I really mean is that if there exists a potential difference between the source and the body, which is not equal to 0. Okay, so this condition means that there is a potential difference between the source and the body. So in turn, you would have studied that the threshold voltage of a transistor would then get modified, and that is written as VT naught plus something like gamma square root of 2 phi f plus VSB minus square root of 2 phi f. Okay. Now this 2 phi f is basically a quantity that comes through some sort of built-in potential phenomena. Okay, so sometimes what happens is that they tend to write it as phi s, and that is nothing but equals to 2 phi f. Okay, the only thing that you need to note here is that any value, either it is given in terms of phi f or phi s, do not get confused. Look at the value. If the value is around 0.7 to 0.8, use that value either as 2 phi f or phi s. Okay, so the only thing that you have to be concerned is look for this particular value. If it is within that range, use it. In case if the value is given as 0.4 or 0.38, okay, then you have to multiply by a factor of 2 in order to get the, so then this means what we have given is something known as phi f, and you need to multiply that quantity in terms of 2 in order to get the phi s quantity. Okay, I hope that I'm not confusing you. So I'll just rewrite the same expression in terms of phi s so that both the expressions are conveying the same thing. The way that I would look at both these expressions is by looking at the value that has been given for this phi s or phi f. Clear? If the value is fit within this 0.7 to 0.8, then use that value as it is over here. Okay, so here maybe I should have used it. Okay, so ensure that whatever the value that you are plugging is in the range between 0.7 to 0.8 or even 0.9, it's fine. Okay, so if that is the case, you use it as it is. Else, if the value is given as 0.4, you multiply by a factor of 2 and then plug in that particular value over here. Okay, so that is nothing but it's a kind of threshold voltage of your diode. Okay, across the Pn junction that we have for the between the body and the source region. Okay, so there is always a Pn junction. Okay. We'll not go much in depth about the physics behind it, but the point is that you look for the range of value that is given in your question and use that value accordingly. Okay, yeah, but does this really make sense? Like, I felt really not good when I just looked at this expression as it is. Okay, so what I have done is that I've just tried to create some sort of picture here. Okay, so before I talk about this picture, I just want to emphasize about what do we really mean by the threshold voltage. Okay, the real meaning behind the threshold voltage. Now, a threshold voltage can be decomposed. That voltage of 0.7 or 0.5, whatever the voltage that we have for a MOS transistor, can be decomposed into two components. Okay, a part of the threshold voltage, let me take this as 0.6. Okay, just a kind of number. So a part of this 0.6 voltage, say for example 0.4 volt, okay, is meant to create depletion region first. Okay. Basically, the entire voltage is supposed to be used for creating the depletion voltage. Maybe I would use that term as well. And a slight bit of voltage is required. Okay, so maybe around 0.59 volt I would use. And the remaining voltage that we have could be used to create a thin layer of channel. Okay. These are numbers, just the numbers. Do not fix your mind to these numbers as it is, okay? Because sometimes we always tell when the value of VGS is equal to VT, still the transfer is off, okay? So that is the reason why I'm not trying to emphasize on this particular point that the threshold voltage is meant to create both, basically. We assume that the value of VGS in this case is required for both to create the depletion as well as to create a thin layer of channel, just an assumption, okay? Now, let me just get back the figure here, okay? So I have just created some voltage that is slightly above the value of VTH, okay? So very tiny bit of voltage more than the value of VTH. So now that it has depleted my carriers, which is given in the dark gray color, okay? So it has depleted the carriers and like the majority carriers underneath the channel, and also it has pulled out the electrons. So the electrons are shown as a kind of bubbles, white color circles. I guess the pictures are clear. So if you want, I can enlarge a bit. Okay. So now in order to create this channel, I need almost like 10 electrons to create this particular channel. Okay. And this is the condition that I have when VBS, when there is no potential difference between the source and the body. Okay, so when both these nodes are at the same potential, this is what happens. But the moment I try to apply some sort of potential difference, say for example the source node is slightly higher than the value of 0, okay, then in that case what happens is that there is a positive charge, okay, and that positive charge will pull out an electron out of this particular regime. Okay, so now that the channel is not completely formed because one of the electron is being pulled off from the channel that is created. Okay, now it is left over with just 9 electron. So now in order to create a channel, I need 10 electrons to completely fill this particular zone between the source and the drain. Okay, I need an extra electron. So how will I get that extra electron, which is a minority carrier? So what am I supposed to do?
So increasing VG.
Increase the gate potential.
Yeah. So in that case, I need to increase the value of VG. Okay. So in turn, I can also visually see that the threshold voltage of the device has also been raised up. Okay. Because for this value, I have already created the channel as well as the depleted region. Okay. But just because the VSB is raised higher, it has lost one of the electron, and due to which the threshold voltage of the device has also been shooted up. Yeah, so we are modeling this particular physical phenomena through this particular expression of Vt. Okay, so whenever there is a rise in the potential difference between the source and the body, the threshold voltage of the device also rises. Okay, that is, it loses that electron, and I need an extra voltage to actually create a very thin layer of channel between the source and the body. Okay, so this is something that gives you a visual feel like why the threshold voltage of the device increases the moment the VSB starts rising. Okay, you may also wonder like what happens when you have the reverse condition. Okay, so say for example I have negative and a positive here, then obviously you need a very less threshold voltage. Okay, that's a different story, and when we talk about a digital VLSI design, we will never encounter this condition. That is, we will not have this VSB in the negative direction just because the body of our NMOS structure will be at the ground. Okay, it cannot be pulled to any positive values, due to which our VSB becomes a negative. Okay, so there won't be any such situation where the source is pulled lower than 0 volt. Okay, so that is the condition, and we always encounter an increase in the value of VTH. Okay, so the next thing that we have to discuss is again that is related to threshold voltage, which is known as short channel effect. And there is also one more effect which is called as drain induced barrier lowering. Okay, so again, all the three effects that I've discussed, including this body effect, 1, and the short channel effect, 2, and the third one, which is the drain induced barrier lowering. All these effects are related to the threshold voltage. Okay, now in the case of a short channel device, what happens is that it is the reduction in the threshold voltage with respect to the length of the channel. Okay, so I'll talk about this. Whereas at drain induced barrier lowering, it's a kind of effect of threshold voltage with respect to the value of Vds. Okay, so and the body effect, so which is nothing but it's a study of a threshold voltage with respect to VSB. Clear? So if I'm trying to talk a threshold voltage with respect to VSB, then we call that effect as a body effect. If I'm talking a threshold voltage effect because of the change in the length of the channel, we are calling that effect as a kind of short channel effect. And drain induced barrier is an effect where the threshold voltage of the device varies with respect to VDS. Okay, yeah. So this effect comes into picture only for short channel device, and even the same applicable for this as well. Okay. Now, why does this happen? When we put ourselves into a question, the one thing that we have to note is that we always define that the threshold voltage is only a function of VGS. Okay. A more practical example is that we always assume that a mother is the only responsible to bring up their child. Okay, so this is something similar to that, and this is the assumption that we had before. Okay, but now we know that both the husband and wife has to play a role in bringing up the child. The same similar reason can apply. Okay, so when I get into the short channel, what happens is that, let us look across this first physical thing. Okay, as I said, a threshold voltage has to do two jobs. One of the job is to deplete the charges. Okay, so that was its major preliminary job, and then later it has to pull the magnetic carriers. Now, when I reduce this channel length, what happens is that you can just barely compare these two things, having a very long channel and the one that has a very short channel. Now, if this is an NMOS, we have to have a p-type material, a p-type substrate for both these structures, and the length of this particular channel is quite large than compared to the length of the channel that is required here. Now let us try to draw the depleted region around the Pn junction. Okay, so now in this case we know that the depletion region surrounds the source and the drain. Okay, and we also know that there is a part of the channel is already been depleted because of this Pn junction. Okay, and even here a part of the channel has been depleted already by this Pn junction, but as we compare the length over which the depleted region is created, this is like a very small fraction. So we can approximately say that in order to create a depleted region for this threshold voltage, we always assume that it's a function of only VGS. Okay, so I have to apply enough VGS to create a depleted region under this oxide region. Okay, but when I look here, the length of the channel has already been reduced. Now this Pn junction has already depleted a part of the channel. Okay, and due to which you no need to create a depleted region at these junctions. Okay, all of these charges are being depleted by this Pn junction diodes itself. Okay, so the only thing is that you are left over to deplete only this part of the channel, which requires a very less voltage than compared to deplete the entire length of the channel. Okay, so this is in the case of a long channel, and this is in the case of a short channel. Okay, so hope that it is clear. So due to which the threshold voltage that is required to deplete the charges underneath the channel has got reduced. Okay, so now let us try to plot them physically. Okay, so I just want to plot only the graph, and we will not get into the modeling part as we had for body effect. Okay, so this is my length, and let us assume like we have 45 nanometers. So let me have 45 nanometer, and let me mark almost like 1 micrometer, and all of these lengths are more than that. Okay, so now that when you try to plot this, the threshold voltage will not be a function of a length till a particular technology, but as and when we try to reduce the technology, as I said, due to this physical reason, the threshold voltage of the device starts reducing. Okay, and this is for 45 nanometer. Clear? So this effect of reduction in the threshold voltage, we call that effect as a short channel effect. Okay. Yeah. So now, can you guess what could be the drain induced barrier lowering and how does this impact our threshold voltage? Any idea?
Sir, so that means in short channel effect for 45 nanometers, the VT will be very small in the sense.
Yes.
Here, sir.
Yeah, but actually, if I try to plot the same thing in your cadence, it will not happen. Now, the reason behind is that there is some sort of heavily doped region underneath this layer, which is known as halo implant doping. Okay, and due to which, in reality, you will not have this kind of Cara, but rather, when you try to plot, this is my VT. Okay, so versus the length, the Cara would look weird. You will have a very high threshold voltage, and then you would get something like this. Okay, and the reason why it has become something like this is because of the halo implant. Okay, so we'll not talk too much about this implant, how does it behaves and things like that. But because of this reason, okay, or it can also be called as a pocket implant, because of this kind of effect, you would find that the threshold voltage of the short channel device is not as I proved theoretically something like this. Okay, it is something in another direction, and the reason for this is because of the fabrication that they have introduced. Okay, because as you said, once the threshold voltage of the device becomes very small, it becomes too difficult for us to control the current flow, because we know that the MOS transistor is a voltage controlled current device. Okay, so if we are not having the hold on the voltage, then it becomes difficult for us to control the flow of current between the source and the drain, and due to which there are some fabrication steps that have been taken. And if you want, I can show you even the graph of this, but I think we are running out of time. Probably in the next class, I will show the graph for this as well as the drain induced barrier lowering. Okay, yeah. So now the only question is that I just want to end this particular note with this discussion. What happens to threshold voltage when we have VDS? Say, for example, I take two values of VDS when it is equal to 0 volt, and the value of VDS that is equal to some positive voltage like 0.6 volt or something. And the third one is at 1.2 volt. Now, what happens to each of these voltages? Will the threshold voltage remain the same for all, or will it increases, or will it decreases? Which among these possible physical phenomena can happen? Okay, either constant as VT, or it might increase, or it might decrease. So you have option A, B, as well as C. And I also forgot to tell about one more thing, velocity saturation effect. Maybe after this, I'll take another 5 minutes, and then I will leave the class. But you need to come up with the answers. Which of the physical phenomena can happen?
So due to means by seeing the channel length modulation, it will decrease. No, so VT will decrease.
No.
As the channel will reduce. No, sir.
No. What happens where the moment I increase this potential? If this is my drain, what happens the moment I increase the potential when compared to the body? What happens to this depleted region? Is this Pn junction is reverse biased? Under this
Yes.
it's reverse bias. So I'm trying to increase the reverse bias, means that the depleted region around the segment will also increase. Am I right? So what you're ultimately doing is that you're trying to deplete most of the charges underneath the gate, just because the channel is already small and you're depleting more of the charges underneath this. So what happens to the threshold voltage? A part of the job is already done by the value of VDS. He has already depleted for me. So the only job that is left over is to deplete only this part of the channel. So do I need a very high threshold voltage, or will the threshold voltage will shrink down?
Shrinks down.
Yeah, it would reduce, right? Because, and this effect we call it as drain induced barrier lowering. Okay, but certainly
Isn't it similar to channel length modulation only?
Channel length modulation is about saturation current, but in this case, it is about the threshold voltage is what we are concerned. That is a current equation.
Okay, so but in both the cases, we are just increasing VDS. So like same region is
of course.
increasing.
Yeah. So like the channel length modulation effect, we can observe even for channel length that is greater than 1 micron also. If you look back, the current equation that I've used for the channel length modulation is still a long channel current equation only. Okay, and as you could guess, that as I raise the value of Vds, the value of Vt is also reducing, and this is the physical phenomenon that happens only for very short channel devices. Okay, and we will not really worry about this effect when we are working across a very long channel, like something like this. Okay, so for channel length of this, depleting a part of the channel doesn't make much change, but the depletion of the charges becomes a huge impact when we go for a shorter channel. Okay, maybe the one reason that I can give why we are discussing all of these effects separately means that we always go for linear model. Okay, the reason why we are always interested in linear model is that you know that superposition theorem, right? Say for example, you have some two potentials and you want to calculate the current flow through the device or something like that. Okay, and we know that maybe I'm not having the appropriate circuit conditions here. Okay, let me just try to apply something like this. Okay, or maybe a plus 3 volt or something. So now to analyze the whole current that flows between them, what I can do is that I can, just because the resistance is a linear device, I could model by taking 1 voltage at a time and then try to add up those results in order to get the total current. Okay, so even here it would be always better to model them as a separate functions. Okay, so we are trying to model them as a separate functions, assuming that these transits are somewhat linear, so that I can add up those impacts later on. Okay, so that is what we have studied in the channel length modulation. We never considered any of these effects, and we just spoke about only how the current varies with respect to Vds. Okay, and we just gave us a kind of separate name, something like that. Okay, I hope you're clear.
Yes, sir. This drain-induced barrier lowering, is it dominating only in the short channel? Like,
Yes. This is
okay,
an impact that happens only in the short channel. If the length of the channel is more, as I said, the depletion around this, when we compare to the total depletion, is barely small. Okay, so the fraction of depletion that this VDS creates is a very small, tiny amount. So we generally assume that it's only a function of VGS, and we never consider it as a function of VDS. Okay, but drain-induced barrier lowering says that the VT is not only a function of VGS, but it's also a function of VDS. Okay, so it's a function of both these voltages, and that impact will happen only for shorter channel device. Okay, yeah. So with this note, I'll just want to talk about a very last point about the velocity saturation effect. Okay, so I guess you might be familiar with this equation. Yes. Okay, so this was the equation that we have used, and what happens is that in this case, you could see that there is a denominator term that is also a function of E. So now when I try to plot E versus the drift velocity, it is not a kind of straight line that I can plot. Okay, and I cannot use this straight line where I could write the drift velocity to be equal to mu n times Z of E. Okay, but what happens is that when I try to plot this as a whole, you would get as a kind of curvature, and then it reaches to the velocity saturation effect. Okay, so every time the slope changes. Okay? So this becomes very hard for us to really predict the value of things. Okay, so there is something known as piecewise modeling. So you would have learned the same thing in your Bode plot, right? Whenever you have a pole, the gain of your system will reduce at a rate of minus 20 dB per decade, and you can use this piecewise approximation. Okay,
sir, yeah. Here, as electric field increases, we should get negative, no sir. Negative direction we should get slope, no sir. Because as he increases
no. Yeah. I think all of these proofs I have done earlier. You can just watch those videos why we are getting a drift velocity in terms of this. Maybe we'll discuss about this, because the electric field is running between the drain and the source, and we are using the charge carrier flowing from source to drain. So based on that, we have this negative sign getting changed. But it's basically a function where as I increase the electric field, the velocity also increases. Okay, it cannot go the other way because it has a negative value. Okay, yeah. So now, if at all, if I want to model this as a kind of piecewise model that we have used, like even in the case of a kind of Bode plot, then one could use this piecewise model as Vd that is equal to mu n times that of E when the electric field is less than the critical electric field. Okay, this Vd drift velocity becomes equal to saturation velocity for E that is greater than or equal to critical electric field. Okay, so based on this, we have had some sort of question. Maybe I'll just show you the question, and the answer of this we will discuss in the next class. Okay, so because of this approximation, I could write that the drift velocity is nothing but mobility times the electric field, whereas the other way around is that when the electric field is, maybe I have to switch over this equal symbol here. Okay, then the Vsat would be equal to mu n times that of Ec. Okay, so now one could use this equation where I need to connect both these expressions. Okay, at electric field that is equal to Ec, then Vsat is equal to mu n times that of Ec is what I can write it. Okay, hope this is clear. This is the field that I have for an electric field that is equal to Ec, where I can equate both these quantities. Okay, so based on this, what one can do is that one could rewrite the saturation velocity Vd sat in terms of the critical electric field. Okay, and this Ec is nothing but can be written as Vsat divided by mu n. Okay, so we have this kind of good relation that could be derived just by this approximation. Clear? So there is a small question here. The critical voltage is what you need to compute for the PMOS transistor, and the PMOS transistor has an effective mobility which is given as 38 centimeter square per volt per second. Okay, and as well as saturation which is around 7 into 10 to the power 7 centimeter per second. Okay, and you have to assume that we have an abrupt change in the velocity. Okay, so which means that we are trying to talk about this kind of field, the one at the blue. Okay, so there is an abrupt change from the linear motion to this constant velocity. Clear? So when you have such condition, what is the critical voltage that you have, assuming that the channel length of the transistor is equal to 200 nanometer. Okay, so I want you to work out this particular example. Okay, I guess I have taken too much of time. I'll just stop here.